At this point, we've handled all the cases where the eigenvalues are real and the matrix is non-defective. The defective case is somewhat more interesting. In this case, we have only one eigenvector. As before, if we start in that direction, we're going to stay in that direction. And because lambda 1 equals lambda 2, or we call that whole thing lambda, is positive, that means we're moving away from the origin. Things are getting bigger. What if u are not one of those? So let's take a look at the second term. If t is very large, very close to infinity, then you can see that in the second term, the v1 dominates. That's the eigenvector. So as t gets close to infinity, that term is going to be relevant. We're going to look more and more parallel to v1. If t is very negative, then the second term is going to look like a very large multiple of minus v1. So in this case, what's going to happen? As t goes to minus infinity, we're going to look like minus v1. As t goes to infinity, we're going to look more and more like v1. And how exactly we do that depends on which side of v1 we start on. So we'll get this sort of spiral situation going on, almost a spiral. It's a half spiral. You turn exactly to be parallel or opposite to v1. And again, if the eigenvalue is negative, you just reverse the arrows. You could have figured this out all yourself just by plotting a bunch of different functions. The point here, though, is that this is what matters. What matters is what the eigenvalues look like. It helps to plot the eigenvectors. They help you understand what the trajectories of this system are doing. If you wanted to, you could just memorize this table for each case of the different kinds of eigenvalues you can have. You have a different picture, and just memorize it. That would be one way to do it. We're going to see there's actually a much better way. One case we haven't handled is the case of complex eigenvalues. There's sort of two ways this can happen. One is if the trace of A is 0, which means that the eigenvalues are purely imaginary. In order for that to happen, they have to be complex conjugates, so one is minus the other. Because they're complex eigenvalues, we're going to get a complex eigenvector. We'll call v1 r plus is, and v2 will be r minus is, where r and s, those are real valued vectors. Just as always, they'll look like the exponential of that eigenvalue times that eigenvector. But since all of these are complex, let's go ahead and work that out and see what happens. If this looks familiar, it should. This is exactly how we treated complex valued trial solutions in the scalar case. Notice z1 and z2 are both complex. We want to be able to draw a picture of this, so we need real numbers. So what I'm going to do is add z1 and z2 together. When you do that, the imaginary stuff cancels out, and you just get cosine alpha t times r minus sine alpha t times s. We do the same thing to get another solution. This time we isolate the imaginary part of z1 and z2. Now our general solution is going to be any linear combination of x1 and x2. If you go ahead and plot this, what you'll get is elliptical trajectories. And I'll let you figure out what condition on alpha makes these things go clockwise, which ones make them go counterclockwise. But that's the idea. You get a bunch of ellipses. The origin stays the same, and otherwise you sort of circle around the origin. The shape of the ellipse is determined by these vectors r and s, and the speed and direction of travel is based on alpha. Okay, what if those eigenvalues have a non-zero real part? The only difference here is that when we write e to the lambda 1 and e to the lambda 2 t, we're going to get an e to the at out front. Otherwise, everything's exactly the same. So our solutions look like the same as in the case where a was 0, just we have an e to the at out front. So for example, if a is positive, what's happening, we're taking an ellipse, and as we move along the ellipse, we're expanding the radius. What does that work out to? That works out to a spiral. And that's if a is positive, the spiral goes out. If a is negative, the spiral goes in. Of course, you could have a clockwise or counterclockwise spiral. It just depends on b and what r and s are. So to summarize, just by looking at the eigenvalues and eigenvectors of the coefficient matrix, we know exactly the behavior of each of these systems. As I said, we could try to memorize that list. In the next video, we're going to find out a really slick way to do it.